Alright, so in today's lab we'll be covering resistance and Kirchhoff's rules all at the same time. So first, what we're going to do in one sense is verify and validate Ohm's law. Right? And Ohm's law, sometimes written as V equals IR, the true definition of Ohm's law in the way that we'll actually be applying it today will be resistance is in fact a constant when we take the voltage across that resistor and divide it by the current flowing through that resistor. So this is what we'll essentially be validating when we compare the theoretical resistance to the experimental resistance. Okay, and we're going to do this via a percent difference. So just to refresh yourselves on a percent difference, in our case the percent difference will be the absolute difference between the theoretical resistance minus the experimental divided by the theoretical multiplied by 100% to get ourselves a percent. Alright, so what we'll first do in the experiment is figure out what our theoretical resistances are, including the overall theoretical resistance of either the series or parallel circuits that we're going to be working with. And then we're going to then determine from the voltages and the currents from our experiment the experimental resistance, and then find a comparison between those two, and hopefully they come out to be fairly low. What I would expect, or at least hope to expect, a percent difference that is less than 2%. Actually, let's do 5%. Should be good. Alright, so we'll consider a nice 5%, and anything less than 5% to be good with Ohm's law validation. Alright, next what we'll then do is look at Kirchhoff's rules. And there are two of them. The first one is called the loop rule, which essentially is a retelling of the conservation of energy. So if we have a loop like this, where we have some voltage and some resistance, in this there will be some current that flows in this direction from the positive terminal to the negative terminal in such a fashion like such. Alright, essentially the voltage that's being supplied to this loop should be equal to the voltage that's being used in the loop itself. So in this case, this is the amount that's being supplied, so the voltage across our resistor should be the same as this. And you'll see this as if we put more resistors in series with this particular resistor, we'll see that the total voltage across all the resistors must equal the total voltage that's being supplied. And certainly you can just add up the individual voltages of each of the resistors that we find, and hopefully we come out to something that is approximately equal to the voltage being supplied. So we can essentially say that the algebraic sum of all voltages and voltage drops, so voltage rises and voltage drops, must equal 0. So if we add in more power supplies in series, we would have more voltages. And the more resistors we add in, the less voltage each of those resistors is going to get due to this conservation of energy. Right? And I'll just put parentheses around this to indicate that it's basically a summation over all of this and not just over the voltages, considering that any resistor is actually a voltage drop. And just to be also to add another caveat in this, depending on how you define your loops, these resistors can be then considered a voltage rise, depending on whether or not you define your loop in the same direction as the current or in the opposite direction. If we have, say, a resistor with the current being defined in this direction, and we define our loop in this direction, this R would be a voltage drop. All right. Vice versa, if our current is flowing in this direction and our resistance is like this, and we define our loop in this direction, then this resistor would be considered a voltage rise. Okay, and then conversely, for any power supply that you may add into the circuit itself. So if you're going against this, basically going from this positive to this negative terminal in that direction immediately, rather than going around in a loop, this would be a voltage drop, and this would be a voltage rise from this direction to this direction. All right, so that kind of covers that loop rule. And so then we'll move on to the second rule. Sometimes the loop rule is called the voltage rule as well. And using the similar verbiage, the second one will be defined as the junction rule, or sometimes called the current rule. All right, and this is another retelling of the conservation of charge. Effectively, the current flowing into a junction, and all currents that you've defined as going into the junctions should be equal to all the currents going out of the junction itself. So if we have here, say, a junction like this, and when we set up our diagram of currents, let's call this current 1, 2, and 3, and these will be different than currents 1, 2, and 3 when you go and fill out the worksheet, so don't think of these as the same. We're just using these as just sort of as a demonstration. So what we'll say here is, since we only have one current going into the junction, current 1, define it on that side of the equation, and we have currents 2 and 3 leaving the junction here. So we have current 2 plus current 3 leaving. All right. Now, to be fair, we could have another wire coming off like this, another wire coming off like that, another wire coming off like this, and you can have as many wires as you can possibly fit coming into a junction, but a minimum number of wires going into a junction must be 3. All right, otherwise it's just a straight wire that isn't being split between the two. You can kind of also think about current, the flow of charges through the wire, as if though it's like water going through pipes and things like that. So you can kind of think of even back here analogously, like your power supplies are essentially pumps that kind of push the water through these pipes, and resistors are kind of like just blockages or things like that along the pipe. And junctions could be split off, say the water main splitting off part of the water to like your house and then going on to your neighbor's house, and so on and so forth. So you can kind of think of it in that particular manner if having a more mechanical view of currents and electricity is a little bit easier in that regards. All right, so these are the two rules that we'll be applying in today's lab. The first type of circuit, to remember how to spell circuit, there we go, circuit, is going to be the series circuit. And what we're going to do is we're going to have a power supply. And this power supply is going to supply a constant voltage, and we'll make it 10 volts, or roughly thereabouts. And then we'll put into this series 3 resistors. Oops, and then this should connect back. Something like that. They should connect. We'll have resistors 3, 2, and 1 in this particular fashion, where the current from the positive terminal in our power supply will flow into resistor 1, then continue to flow into resistor 2 and 3, and then back like such. So if we define our current in this particular direction, this is the way in which the current should flow in our system. All right. We can also apply Kirchhoff's rule, the loop rule, and define this as just one loop. So what we would then expect to see is that the total voltage being supplied to the 3 resistors in total should be the same. So if we add up the individual voltages across these resistors, we hope to get approximately the same amount here. All right, but you'll hopefully notice that the current is not being split amongst the resistors themselves. It's the resistors are in series, and the current is flowing equally into each of these resistors, and hopefully what we'll see in the demonstration, that the current is the same in each of those resistors. All right, so if we were to find a total resistance of this circuit, say if we combined this resistors 1, 2, and 3 into a total resistor R sub S, if we first apply the loop rule that we discussed before here, that the sum of all voltage rises, subtracting off all of our voltage drops, should give us 0. So let's do that. All right, so we've defined our currents flowing through R1, R2, and R3 as I, and our voltage V will be the same between the two. So here, from this particular drawing, we have voltage V, minus current flowing through R1 times R1, minus current times R2, minus current through R3, and as we said, this should equal 0. All right, so if we then set the power supply on its own and the other resistors on the other side of the equation, we get this equation here. And since I is common to all of them, we can factor that out, and we get I times the quantity R1 plus R2 plus R3. All right. And from our combined setup here, this will come out to look like this. All right. Since this V and this V are the same, that leaves us now with this. I is the same here and here, since the current should remain unchanged in this particular setup. This is R sub S. So then we can then write R sub S is equal to R1 plus R2 plus R3. All right. So you may be familiar with this before from other discussions about currents and resistors. You may have seen this in other demonstrations as well. So one thing to note as a check, so if we do a check, RS must be greater than the largest individual resistor in series. Okay. In our demonstration that I'll be performing here in just a moment, R sub 3 will be the largest individual resistor, so hopefully your R sub S will be bigger than R sub 3. And that makes natural sense as we're just adding all the resistors up together. All right. Finally, we'll look at one more circuit, and that circuit will be an entirely parallel circuit. All right. And so we'll have our power supply like such. And we're going to create two sets of junctions. Like such. All right, this will be our power supply, again supplying 10 volts. And we'll have resistor 1, resistor 2, and resistor 3 hooked up in this fashion for our setup. All right, so in this setup, we'll have actually 3 different loops. And so we'll have a current coming out that we'll just call I sub P, I sub P for parallel. And that total current will split off into I sub 1, which will be supplied to resistor 1. And then we'll have another current, let's call it I prime for right now, that will be then supplied to resistor 2 and resistor 3. All right. That current should then flow through resistor 3 like such, unchanged, and then recombine with current 2 to then hopefully recreate I prime, and then I prime will then hook up, reconnect with I sub 1, hopefully giving us back I sub P. All right, so if we apply the junction rule here, if we come to our first junction, let's call this A and B and C and D, we'll actually see that C and D actually correspond to B and A respectively. So depending on which side you want to look at, it should be the same for this particular setup. So just be aware that the way that you might define particular junctions in your setup, they may actually come out to be the same as other ones due to symmetry of the problem. So just be aware of that. All right, so let's look at A. A, we have I sub P, and I sub P is splitting off into I sub 1 and I prime. Okay, so that's our first junction. Our second junction, B, gives us I prime equaling I2 plus I3. All right. I prime is common between these two equations, so if we rewrite this, we can write I sub P just equals I sub 1 plus I sub 2 plus I sub 3, and just neglect I prime here. And we won't even measure this in the demonstration, but if you were to actually do this yourself, if you wanted to, you can always validate that yourself. But hopefully what we'll see is that the total current going into our system is equal to the individual currents going through each of the resistors. So that's our one equation that we got from the junction rule itself. Next, we have the loop rule. And here we'll have multiple loops in this particular setup. So here I'll draw a blue loop like that, a second loop like this, and then finally our third loop, which goes around like that. So if I label this as 1, 2, and 3, I'm kind of getting a little cluttered there. But hopefully you've been following and everything is okay for now. So we'll do loop 1. And in loop 1, we have the voltage equaling the current that's flowing through the only resistor in our loop, which is R1. So we have I1 plus, times, this should be times R1. So let me rewrite that like such. And in loop 2, we have a similar situation. V equals I2 R2, and loop 3 we have V equals I3 R3. Now if we were to create similar setup with just a single resistor, and we call this resistor R sub P with the same voltage V, we can then find what the current is, or what the total resistance is, based on the fact that we know that the current that's coming into our system if we were to measure that. So let's apply that in the same way that we did with the series circuit, and hopefully we get an equation that allows us to figure out what the total resistance of this particular circuit is, just based on the resistance of the individual resistors themselves. So let's do that. All right, so let's see here. We got I sub P equals I1 plus I2 plus I3. All right, and from Ohm's law, if you recall, R is equal to V on I, or I is equal to V on R. All right, so let's use this in here, and so we get V on, RP equals V on R1 plus V on R2 plus V on R3. You'll notice here that since V is the same, or we're using the same voltage again, this would be common. We can factor out the V and then divide both sides by V, and we'll get the infamous 1 on R. So P equals 1 on R1 plus 1 on R2 plus 1 on R3. Now remember, in order to use this equation correctly, you need to take the inverse of the individual resistors themselves, add that together, then take the inverse of that addition to then find R sub P. Okay, so it's going to be a little tricky in that particular addition of resistances to find R sub P. All right, and again, this also has a note for a check, and that check is R sub P should be less than the smallest individual resistor in parallel. Okay, so hopefully that sort of covers the basics of using Kirchhoff's rules in these equations and what we'll eventually be doing in the demonstration and calculation from our experiment. All right, see you in just a moment.